Gracias. Thank you. Thank you, everyone. Thank you for inviting me to today in this important event. Today, I will talk about the cytotoxicity effect of functionalized electrospun nanofibers. So, as my presenter just mentioned it, I'm from Mexico. I am located in the US border between San Diego and Tijuana, Baja California, Mexico. This is my institution here. So today I will give you some introduction. I will explain to you the electrospinning technique. That is the technique that in our lab we are using to prepare nanofibers. That I will explain that later. We will talk about some methods for incorporation of bioactive molecules on fibers, about the bioactivity of these functionalized fibers. I will give you some future work while we are working right now and some important remarks. Well, first of all, what is the electrospinning technique? Well, it's a technique, a very simple and versatile technique that is dedicated to fabricate electrospun fibers. These fibers are in the nanometers range, and you can load it with different bioactive molecules, such as plasmids, proteins, drugs, some natural molecules, vitamins, and so on. And this technique has a shrink pump. You can load a polymeric solution that has to be conductive. You put it on the shrink pump, and you will inject this polymer solution in a certain rate, milliliters for hours. Then you will use a metallic collector in order to attract the future fibers, and you will use a high voltage supply. So you will connect an electrode in the stainless steel needle and another electrode in the metallic collector that usually we use aluminum, but you can use different kind of metals. Because we prepare these nanofibers for biomedical applications. For us, the best option is to use aluminum. And then when you apply the high voltage supplies and you inject the polymer solution, that the polymeric drop in the needle get attracted to the collector and created, it is created the fiber in the air, and the solvent that you use to dissolve the polymer evaporates, and the fibers is collected randomly to the collector. So you will have a three-dimensional structure that you can see it in this same image. Why electrospun nanofibers are interesting? Well, you can prepare these nanofibers in the nanometer scale. Even there are some few articles that are reported fibers less than 10 nanometers. With these nanofibers, you can create mats, as you can see it on the right side, and they will have a high surface area. This means more contact sites in a minor spatial radius. And this property can be controllable. You can also control the pore size. You can prepare these mats with low density. You can use biocompatible polymers, biodegradables. These final products can be flexible, elastic, with desired mechanical properties depending on the applications. And if you load some bioactive molecules, you can prepare mats with a bioactive functionality. So here in this slide, you can see some GIF where you can see how the electric field is attracting the polymer solution and creating fibers in the air and are collected in this metallic collector. And if you compare the human hair with these nanofibers, you have this comparison in size. No? Also, you can use some rotatory drum collector, and you can collect the fibers in the pattern, a well-defined pattern, as you can see it here in this GIF. So at the end, we want to obtain a three-dimensional structure. Sorry, you can obtain a three-dimensional structure. I'm sorry, this GIF it doesn't see very well. Okay, but these Electrospun nanofibers can be used for several applications, such as tissue engineering, drug delivery systems, biotechnology, and organic solar cells, just to mention some applications, because there are more. But I mentioned these four because these four applications we work in our lab. In the case of tissue engineering, these nanofibers simulate the extracellular matrix of tissues. So this promotes the proliferation rate of the cells. You can prepare these fibers, and the tissues will, you can differentiate the tissues using mechanical and biological properties, no, of these nanofibers. You can customize the surface of the fibers, so you can promote proliferation, you can promote migration, or other, or for example, stimulate the cytokine production, and so on, no? Depending of what you put at the surface of the fibers. These fibers can be biodegradable and bioactive. That in the case in tissue engineering. In the case of drug delivery system, you can control the doses of the drug that you load on the surface, and that will depend of the final application. Sometimes for this kind of administration, it is desired in children's and geriatric patients, because you can put the mat, the scaffolded mat at the tongue or below the tongue, and then these fibers can degrade it in seconds, releasing the pharmaceutical drug to the vascular system. It is practical for transportation and storage, and usually is proposed for local and oral administration. In the case of wound dressings, this is one of the topics that we work harder. Keeps faster cicatrizations, mechanical and biological differentiations, and the important thing that you can load antimicrobial properties. Antimicrobial properties in order to avoid bacterial infections and promote cicatrization of a skin wound dressing. These fibers also can be used to become an ambient protective layer. You can prepare fibers with bioadhesive properties and give moisture to the wound. And finally, we also work in implantable organic solar cells, where you can load bioactive molecules that enhance electron transfer. Depending on the polymer used, you can customize the mechanical properties. And this is very interesting because you can enhance, or you can increase the surface area where the analyte of the photons that comes from the sun can be captured by these fibers. You can prepare fibers, biocompatible fibers, and with lightweight. So this is not it's not going to create any
which condition
in the tissue of the patient.
Parameters
Here, the Electrospun fibers is not that easy. It's easy, but you can take account different parameters to create beautiful nanofibers, no? Well-defined fibers with reproducible properties. You can take account the molecular weight of the polymer concentration. You can select the correct solvent to give conductivity to the solution, and you can work on the surface tension of the final solution. In the case of the parameters of the electrospinning process, you need to vary in the applied voltage, the collector distance, the flow rate, and the type of collector. Depending on the collector, you will have the distribution of the fibers, and depending of these parameters, you can have thinner fibers or thicker fibers, depending on the application that you want to work. And also, we have to take into account environment and ambiental parameters such as temperature and humidity. If you don't control these parameters well, you will have thicker fibers, or even you will not be able to create fibers. Here I can show you some of the fibers that are creating in the tip of the needle. So you can see how the fibers are creating. You can see that the fibers forms in multiple fibers are formed from the electrical fields, and you can create a multi-layer systems, as you can see here. This one you can load it with pharmaceutical drugs or other interesting molecules. How many of Electrospun fibers? How many of electrospinning techniques are? There are a lot of electrospinning strategies in order to load bioactive polymers, molecules, or you can conjugate or blend different polymers into the fibers. You can have the bioactive molecule inside the fibers or between the fibers, depending on the electrospinning technique used. Or you can load, for example, nanoparticles, and you can load it to the surface of the fibers. You can prepare, first of all, the fibers, and then with another technique, you can coat the surface of the fibers. Or there is a coaxial electrospinning where you have a core shell fibers, and you can put labile proteins, for example, or living cells into the fibers. There are some reports that some researchers in France has been electrospun living cells, living mammal cells into fibers, and they check the viability after the process. In the case of to have bioactive molecules between fibers, there is a direct blending electrospinning. This is very easy technique where you put the bioactive compound solution into the polymeric solution and then prepare the electrospinning process and create the fibers. You can have also the coaxial electrospinning where you use a special shrink where you have two holes. In the inner hole, you have the bioactive molecule, and the outer hole, you have the polymer solution, the polymeric solution, and this is intended to protect from environment the bioactive molecule that can be liable to temperature of light or electricity. You can also prepare nanoparticles or nanogels or other molecules that doesn't dissolve into the polymeric solution and create an emulsion system. And then you load it, and you can have a fibers with these kind of nanoparticles on the surface of the fibers. Also, you can prepare the fibers, or you can coat another kind of devices, bigger devices, such as catheters or other kind of biomedical devices, and you can load it with nanofibers or nanoparticles. So this electrospin technique can also coat surface with nanoparticles using the electrospray strategy. The only difference between the electrospinning and the electrospray technique is the use of lower viscosity in the solution. If you want to create fibers, you use high viscosity solutions, and if you want to have particles, you prepare with lower concentrations of the polymers. And also, finally, you can have a coaxial electrospray where you can create nanoparticles, but with a core share morphology. Right now, we are working to load silver nanoparticles into the fibers using different techniques. And that is important to us because we have a big group that works with silver nanoparticles, and we already have been publishing a lot of silver nanoparticles, and it's used in different tissues or different cancers, cell lines, and even in some hospital we have been trying the use of silver nanoparticles into the diabetic food of patients. So in my case, in my part, I have the idea, or we have the idea, to load these silver nanoparticles into the fibers, but we found that there is several strategies to load these silver nanoparticles into the fibers. Mainly, we found 4 different methods, and we searched in literature, and we found a lot of literature that works with these 4 methods, but they do not report the same conditions, or they do not characterize with the same techniques, and that's the necessity to compare these 4 methods with the same conditions, and to see which one of these methods is the best. The first method is the easy one. You can prepare the silver nanoparticles with other method, and just you put it into the polymer solution, and then you make the electrospinning, and you can have the silver nanoparticles between the fibers. The main problem of this technique is that you have agglomerations in the fibers of these particles. We have other 2 methods very similar to the first one, but you use thermal treatment or UV irradiations after you prepare the fibers, and you put it into a nitrate silver solution, and then you irradiate with UV or with thermal treatment. You can reduce the silver nitrate. You can reduce it over the fibers, and you can have a very well coated fibers with these silver nanoparticles. And also you can use reducer agents when you create the nanofibers. You put it into the silver nitrate, and then you add extra regions in order to reduce this compound into on the surface of the fibers, and you can also load the surface of the fibers with these final silver nanoparticles. After we try that, I will show you several works, several experiments that we have been working with several postgraduate students. We always fabricate the fibers and then make a physicochemical characterization using SEM, FTIR. We also use TGA and DSE, meaning thermal characterization. And we also use cytotoxicity testing that I will discuss with you later. But the idea to load bioactive molecules on the fibers is in order to release these bioactive molecules and give some effect into the cells. So mainly the fiber itself doesn't promote any alteration, but can mechanically differentiate a cell. But usually when we want to promote any bioactivity, we load the fibers, and this bioactive molecule will release to the fibers and will release to the tissue and perform a cellular mechanism as I put in these examples. Also, it's important the fibers to create the three-dimensional structure in order to have a high surface area so that the cells can stick or can interact with the fiber surface, and this will promote proliferation because this is simulating the extracellular matrix of the tissues and will promote cell replication by adding this scaffold. We usually, in order to test the cellular response to the Electrospun nanofibers, we usually use fibroblasts, mouse and human fibroblasts, and we usually use the MTT assay. This MTT assay uses a dye that is reduced by a mitochondrial enzyme named succinate deshydrogenase and creates an insoluble compound named as formazan crystals. So you can see here at the right these formazan crystals that are dissolved with DMSO, and then you can detect by colorimetric spectroscopy at 600 nanometers the concentration of formazan present into the cells. To do this test, we expose the cell lines to the fibers for 24 hours. After these 24 hours, we take apart the cells and then we add the dye. So we then wait for 4 hours, and if the cell is alive after being exposed to the fibers, the mitochondrial enzyme will work very well and will create high concentration of formazan. So when we have a high absorbance value, we can say that the cells are viable after the exposure onto the fibers. And if we observe a decrease in the absorbance, we will relate it to the loss of viability after being exposed to the fibers. Always comparing with the normal growth without any exposition into the cells. So from one of our experiments, we have here polycaprolactone, polyvinyl pyrrolidone fibers loaded with silver nanoparticles. And here I'm showing different kind of fibers prepared by the 4 different methods that I showed you before. We obtain different fibers with different diameter average between 700 nanometers and in average. And as you can observe, these fibers doesn't create or doesn't alter any doesn't alter the cellular replication of human fibroblast HFF1. We can have some loss of bioavailability in this when we use thermal treatment in these fibers and when we use a UV treatment. So, but if you compare all the fibers, we don't have too much loss of bioavailability after 24 hours of exposition. In order that when you have a mostly 80% of bioavailability, you can say that the fibers are not that toxic. These are desirable results because because if you want as a cytotoxicity, you will expect below 50% of replication of the cell growth. We have other kind of fibers, but these I'm sorry. These fibers, we want to propose it for wound dressings because silver nanoparticles have been published a lot that has several antimicrobial activity. So I will discuss that in other slide, but because of that, we want to propose these fibers to the wound dressing application, being this UV treatment, this one, and this silver mirror reaction treatment, one of the 2 potential scaffolds in order to prepare other experiments to promote this application in these fibers. We have another system where we use polyvinyl alcohol. This polyvinyl alcohol polymer is highly degradable, so it can degrade in 7 minutes. So it is used for drug delivery system. In the last case, this polycaprolactone it degrades in 6 months, or can be degraded in 6 to 8 months. So you can use it without any problem with degradation for wound dressings. But this polyvinyl alcohol degrades in 7 minutes at most. You can, if you use less molecular weight, lower molecular weight, you can improve the degradation rate of these fibers, and is intended to release propanolol, the propanolol drug. And in this case, we tested also with human fibroblast cells, and as you can see, no much alteration in the cell viability can be observed. With the fibers, these 10, 15 are the percentage of propanolol loaded into the PBA fibers. So as you can see, no much alteration of the cell viability can be observed with these fibers. What I'm trying to say here with these 2 examples of our experiments, that if you use the correct polymer for certain application, you will not have any tissue response. Of course, you will have a tissue response, but is is like. You will have a slight tissue response and will not alter the health of the tissue where you are applying these systems. These fibers are thinner. As you can see, the fibers are of 200 nanometers, 300 nanometers are thinner compared with the polycaprolactone fibers. And you can also control the porosity. In the case of antimicrobial activity of these nanofibers, in the case of the silver nanoparticles, there are many publications that works or test mechanical mechanisms. I'm sorry, cellular mechanisms of silver nanoparticles, and it's highly reported that silver nanoparticles disrupt the membrane integrity, can also alter the DNA replication or join to the thiol groups or promote the creation of ROS molecules. The idea to load silver nanoparticles to the fibers is in order to the fiber to release these silver nanoparticles into the wound, into the open wound, absorb the liquid or the exudate that is created in the skin wound, and cover the wound from the environment, give moisture, and avoid bacterial infection in these wound dressings, and promote migration and proliferation of the epithelial cells. In the case of the antimicrobial activity of these silver nanoparticles, we have these fibers with silver nanoparticles with 16 nanometers, 100 nanometers, so very, very small silver nanoparticle sizes. Compared to literature, they publish silver nanoparticles loaded into the fibers with 13 nanometers and so on. So we have good results in these experiments. And as you can see in this antibacterial testing using a microdilution test using the Staphylococcus aureus and E. coli, you can see how the presence of the loaded fibers after 24 hours, 48 and 72 hours, you can see how these fibers creates much alteration in the cellular replication of this bacteria, avoiding the replication of less than 50% of the growth in Staphylococcus aureus, and 60% less in E. coli. So that's our desired results for this application of wound dressings. At the contrary, we can also use the fibers to promote biofilm formations and promote proliferation of the cells in order to extract some interesting metabolites from bacteria. If you use the correct polymer and the correct bioactive molecules, you can promote, instead of kills bacteria, you can promote the bacterial proliferation in order to extract more metabolites. In this case, we use the polycaprolactone fibers loaded with low concentration of ethanolic extract of curcumin. Curcumin is a well-known molecule toxic to the cells, to the bacterial cells, but with certain preparation and low concentration, you only cause stress in the cells, and when the bacterial cell is stressed, promotes the biofilm formation. So you can see here, for example, in this Staphylococcus aureus SEM microscopy, you can see how the three-dimensional structure of the fibers creates a scaffolds to promote the biofilm formation of this Staphylococcus aureus. There are other systems that we are working, for example, using gelatin and collagen from fish. And also, we tested to bacteria. And the idea of this slide is to show you that in certain bacteria, you can have a decrease of the percentage of proliferation or an increase. Not all bacteria responds with the same not all bacteria responds in the same way to the presence of the fibers, depending on the formulation that you use, of the morphology of the bacteria, that when it's some bacteria needs movement and some other has different molecules in the cell wall. So all that will creates variables to see how will respond to the different formulation of the fibers. For future work, we want to optimize the mechanical properties of the fibers. For example, in wound dressings, we want high mechanical properties, meaning a high deformation force is needed in order for the user can manipulate this fiber easily. But in other applications, such as drug delivery systems, we need a certain mechanical properties in order that the user can take it, put it into the tongue of the child, and degrades easily. So we need to work between an equilibrium between the average diameter of the fibers and the mechanical properties of these systems. We also, after we are testing with in vitro testing in different cell lines, we will work in vivo testing using the implantation in subcutaneous tissue in rodent animals. We have a veterinary collaborator in our group, and we want to quantify cytokines in order to and prepare immunohistochemistry slides in order to see mechanisms of actions in cells and see the intensity of the immunological response of tissues in the presence of the fibers. The important remarks here is that the electrospinning technique permits the fabrication of bioactive and biocompatible fibers for different biomedical applications. There are different strategies in order to load bioactive components at the surface, between the fibers, or inside the fibers. And the biocompatibility of the polymeric fibers can be seen with bioactive components. And also, these fibers can possess antibacterial cytotoxicity and are well studied in the literature. So this is the work team of our lab, and thank you very much. Any question?